So in this exam question, it comes under the topic rate equations, but it's primarily focused on, or is significantly focused on, required practical 7. That's really why we're looking at this particular question. So we have, at the beginning, we have quite a lot of text, and it is important that you read all of this carefully. And I know that's difficult to do in the heat of an examination, but all of that information could be relevant, or any of that information, could be relevant to any of the questions that follow. And in some cases, the questions that follow won't make any sense without really understanding what's written here. So we have a reaction of hydrogen peroxide and an acid and iodide ions, and they produce iodine and water. And they give us the rate equation. And we have unknown orders with respect to the hydrogen peroxide. So it's A at the moment, the iodide ions B, and the H plus ions C. And then it says, in an experiment to determine the order with respect to H plus, a reaction mixture is made containing hydrogen ions with a concentration, and they give us a concentration. Then they say a large excess of both water and iodide is used in this reaction mixture so that the rate equation can be simplified to, and we'll notice that you've got a different looking rate constant, or at least it's supposed to represent something different. It's still a rate constant, but it's representing something different. We've got K1 as opposed to just K. And we now just have the concentration of H plus ions to the order of C. Now this is the actual, or this is probably the reaction that you did for your required practical 7. And I think, if I'm right in thinking this, the AQA version, which is this reaction, has you focusing on changing the concentration of iodide ions. So it's the same reaction, but what they've done is, whereas you were changing the concentration of iodide ions and trying to work out the order of the reaction with respect to iodide, in this one it's with respect to H plus. So if we just unpick this a little bit, so this is required practical 7 in effect. Now the key point here to appreciate is this largest excess, because that's going to explain why we can go from this to this. And if you think about it, when you compare those two rate equations, and they've said it's been simplified, then what they're saying is that K1 equals K concentration of the hydrogen peroxide to the power of A, and then the concentration of iodide to the power of B. So all of this is found here, right, in our K1, because if you compare what you've got here to what you've got here, it must be all in that K1 there. So how can they do that? Why are they able to do that? So the key is this large excess. Now, they haven't just said excess, they've said large excess, and that's very important. So if you think about when you're doing, if you think about how science works that you've done throughout school, you have an independent variable, you have a dependent variable, and you have control variables. And we are trying to determine the order of this reaction with respect to H plus ions. So the concentration of H plus ions is going to be our independent variable. We are going to change the concentration of H plus ions, or we're going to let the concentration change over time. And we're going to see how that affects the rate of the reaction. So the rate of the reaction is going to be our dependent variable. So that means everything else has to be controlled. That means the other reactants have to be control variables. So how do we ensure that that is the case, given that they've got to take part in the reaction? Well, the way we do that is to have them in large excess. So I'm slightly preempting the first question, but imagine our three reactants are 3 people. Okay, person A, person B, person C. And they're each going to, in the reaction, they're each going to spend £1. I know it sounds a bit, just bear with me on this. So A is going to spend £1, B is going to spend £1, and C is going to spend £1. But we've made A and B in large excess. So what we're saying in effect there is they're millionaires. So let's say they each have £1 million, but our H plus, or C, our person C, still only has £1. Now, if they both spend £1, we've gone with A and B, we've gone from £1 million to £999,999. In effect, the amount of money they have has hardly changed. The change in the amount of money that they have is negligible. Whereas person C, which will be H plus in this case, they've spent all their money. They've gone from £1 to £0. And so that is really what we're talking about when we're saying large excess with these reactants. We have so many more moles of the hydrogen peroxide and iodide ions that when the reaction is finished, the concentration of those two substances has hardly changed. And that is how we are able to treat them as control variables. So the first question says, explain why the use of a large excess of hydrogen peroxide and iodide means that the rate of reaction at a fixed temperature depends only on the concentration of H+. So why is it that these are, in effect, control variables? Well, it's because the change in their, or we can say their concentrations, are effectively constant. So, the concentrations of the hydrogen peroxide are effectively constant. So that's one mark, but we've got to also sort of explain why that's important. So they have no effect on the rate of reaction. They are control variables. Something else to just point out, when you look at the actual question, they mention this large excess again. They're really trying to draw your attention to it. So, that's really how this reaction is working. This is how we're able to have three different reactants that may or may not affect the rate of reaction, but they are certainly in the reaction. How can we measure the rate with respect to just one of those reactants, given that we know we can only have one independent variable, everything else has to be controlled other than our dependent variable, and that's how we achieve it in this particular example. Right. Okay, so then it says samples of the reaction mixture are removed at timed intervals and titrated with alkali to determine the concentration of H+. State and explain what must be done to each sample before it is titrated with alkali. Now, I don't know what the timed intervals are, but let's say they're every 60 seconds. So we start the reaction, and then every 60 seconds we want to be titrating our sample to determine how much H+ is left, so that we can then later on plot a graph of concentration against time. In fact, that's going to be the next part of the question, concentration against time. Now, if you think about what you're actually physically would be doing here, you would have a reaction mixture, you would be taking a sample at 60 seconds, and then you would be having to go through the whole process of doing a titration. Now, just because you take a sample, from the reaction mixture, does not mean that the reaction stops in your sample. The reaction is just going to keep going. Just because you've taken, let's just say 2 centimeters cubed let's say 20 centimeters cubed. Let's say you've taken 20 centimeters cubed of your reaction mixture and you've put it in a different beaker because you've transferred it, or into a conical flask because you're going to do a titration. The reaction hasn't stopped just because you have removed it from the original reaction mixture. It's just going to keep going. And yet you want to know what was the concentration at those 60 seconds. So what you have to do is you have to stop the reaction, or in effect stop the reaction at that point, at the moment that you remove it. Now, there is a word that we use that describes that action, and it is quenching. So you need to quench the reaction. Now, again, just to sort of make it clear what that means, in effect, that means stopping it. Now, then we have to explain how we're going to do it. So stating it is the quenching it. Explaining it is how we're going to go about quenching. Now, if we were trying to determine the order of reaction with respect to either hydrogen peroxide or iodide, then what we could do is we could, if we know there's an acid catalyst, one of the things that we can do is that we can remove the acid catalyst, and we would do that by adding something like sodium carbonate. So there has been a question once where it asked, it was a rate equations question, and it said why was sodium carbonate added before the sample was titrated, and in that particular example it was to basically remove the catalyst and in effect stop the reaction. We can't do that here. We can't add sodium carbonate because that would react with the H+, which is what we're trying to find out the concentration of, or find out the number of moles of at this particular moment in time. So the sort of safe, if you're just having to give any method for quenching, then really a good go-to is to cool it. So if you put it in an ice bath, we'll write that in an ice bath, but I think by cooling it is enough. Then temperature has a significant effect on the rate of reaction. So putting it in an ice bath, although it doesn't actually stop the reaction, it will slow it down to the extent where you can basically take a reasonably accurate measurement of the H+ ions at that point in time. The other option, or the other fail-safe, is you can dilute it. So you add lots of water, and because what in effect you're doing is you're making the concentrations by diluting it, you're making the concentrations much smaller. Therefore, you're hopefully in effect, so you need to dilute it quite significantly, you're hopefully in effect stopping the reaction. And because in a titration what you're actually measuring is the moles, you're not going to change the number of moles of H+, so you can still take an accurate reading. This is one of the reasons why you can rinse a conical flask in a titration with water to make sure that, or to run water down the sides of a conical flask in a titration to make sure all of the reaction mixture is mixed, because what you're actually measuring is moles. So by diluting it, we are not affecting the moles of H+. All right. So quenching is the action, and always work methods will be cooling or diluting. But just bear in mind, they may mention a method of quenching which is using sodium hydrogen carbonate or sodium carbonate. And in that instance, almost certainly, but you obviously need to look at the reaction to check, it's neutralizing an acid, and therefore that's the way the reaction is quenched. Okay, so then they've given us a graph of results for this particular experiment. So this is another thing, when they're doing required practical questions, yes, it can be about the method, yes, it can be about the principles and equipment, but it can also be about the results and how you use those results. So it's a fairly broad term sometimes as to what really is a required practical question. But they've asked the question here. They've given us concentration against time. So there are 6 graphs, 6 graphs, perhaps 7, that you really need to be familiar with. You need to know the 3 concentration versus time graphs for 0, first and second order. You need to know the 3 rate against concentration graphs for 0, first and second order. And then I'd argue that you need to be familiar with rate against concentration squared and what that might look like, because that has come up, I think, at least once. So it's asking to explain how the graph shows that the order with respect to H+ is 0. So we're not having to decide that it's 0. We don't have to, in a sense, that would be a recall going, oh, look, I know the shape of that graph, that's a 0 order. So we have to explain how we understand that is 0 order. And the thing is, to determine the rate of a reaction, at any particular moment during the reaction, we draw a tangent at that particular concentration. So if we want to know what the rate of reaction when the concentration is 4, we would draw a tangent. 0.4. If we wanted to know when it was 0.2, we would draw a tangent. And remember, what the tangent is doing is it's giving us a gradient at that point on the line. Now, that gradient is the same all the way through. So that piece of information is telling us this is first order. So there is a constant gradient Now we have to explain what that gradient is referring to. We can't just leave it at that. You can see it's 2 marks, so we need to say 2 things. So there is a constant gradient as the concentration, because that's what we're focusing on, all right? That's what this information is telling us, as the concentration of H plus decreases. So changing the concentration of H plus does not affect this gradient. Therefore, the rate is not affected by this gradient. Okay, so rate is always the change in something over time. Our gradients are the change in concentration over time, and the change in concentration over time is not changing in this reaction with respect to H plus. Then it asks us to, and reading graphs doing gradients are going to come up at some point, but use the graph in figure 1 to calculate the value of K1, give the units of K1. So the first thing to say is, and you can see I've already done my dashed lines, I wasn't going to bore you by drawing those on. I think you make your life easier when doing gradients if you can go, and it's not always possible, but if you can go to the axes. Because I already know that this is 0, I only have to read this value, and I only have to read this value to know my changes in x and my change in y. I think if you do other things like that, then you're having to work out, well, what's that point, what's that point, what's that point, what's that point, and you're just making your life a little bit more difficult. So if you can, use the actual axes, because chances are it's much easier to read, and if it's much easier to read, then you're much less likely to make a mistake. So when we're working out a gradient, our gradient is always the change in y over the change in x. And if I look at my graph here, I can easily see that I go from 0.5 to 0. So my change in y is, well, it's actually minus 0.5. And then my change in x is again from 0 to, and you've got to be able to read that carefully. So I think that is 415. If I zoom right in, you can see that that is halfway along that second square. So it goes 400, 410, 420. So that is 415. Okay. And then I know that because I can do the units as part of this. So the concentration is moles per decimeter cubed, because that's the unit of the concentration. It's labeled on the graph. So do bear in mind that they quite often give you the information that you need. I'm dividing it by the change in x, which is in seconds, so time. I do that sum. Now, when it comes to rates, I've done the change in y being minus 0.5, and the reason I've done that is because I think you need to remember for other questions that you can have a negative change. However, when you're doing rates, literally rates, you can't have a negative rate. I mean, clearly, we're just focusing on the rate of reaction. So actually, in this instance, the minus value, the negative value isn't important. If you did include it in there, I'm pretty sure they would just say ignore, which is fine. But I did just want you to remember and recognize that you can have negative gradients. And on things like entropy questions, where you're doing delta S, the gradient is minus delta S. And on the activation energy questions with gradients, you do need to remember about negative gradients. But anyway, I do that sum and I get 1.20 times 10 to the minus 3. And then I can see that my units are moles per decimeter cubed, seconds to the minus 1, because this is 1 over s, or s to the minus 1. So moles per decimeter cubed, seconds to the minus 1. The other thing to say is because we said it was 0 order, or because we concluded it was 0 order, that meant that rate equaled k, or k1 I should say, right? So because we're working out k1 here, and the units of rate are always moles per decimeter cubed, seconds to the minus 1. So we've sort of proved that now, or shown it, but because our rate equals k1, because our H plus concentration was 0 order, so that means this is 1. So rate equals k1, then yeah. Okay. Moving on. So here it's another graph question. What they've done is they plotted, so again, so that you didn't have to be bored with me doing my different points and everything. They had plotted, I think it was these 3 points, and then you had to use the rest, sorry, from here I think it was, the rest of the values, and you had to plot them, so that's 1 mark. They will be quite strict about, that your accuracy in plotting those points. Then the next question says, draw a line of best fit, and I really, really hope that you felt it was obvious that if you look at my blue line, that is a curve. I mean, in science, lines of best fit can be a curve or a straight line, but really the point should make it clear to you which of the two it is. Okay, so 2 marks, 1 mark for plotting the points, 1 mark for drawing a line of best fit. I mean, they should be a gift, really. And then it asks us to calculate the rate of reaction when the concentration of hydrogen ions is 0.35 moles per decimeter cubed. Show your working using a suitable construction on the graph in figure 2. So you would have both of these pages, that one would be the left-hand side and this would be the right-hand side. So you would have everything sort of in front of you. Now, when they ask you to work out the rate at a particular concentration, then what you're going to be doing is drawing a tangent at that concentration. Now, a tangent is a line that touches, it's a straight line that touches a curve at one specific or one particular point. So really what you're doing is you're working out the gradient of the curve at that particular point. So we are going to be drawing our tangent at 0.35 moles per decimeter cubed, and that's what I've done. All right, so that's my green line. My green line is my tangent. So you may feel it's not perfect. It's quite hard to do actually on this iPad to do it as well as I would like. But I'm hoping there's our 0.35 point. I'm hoping you feel that that line looks as much as it can do, that it touches the curve just at that point. And you'll notice that I have extended the line so that it reaches the y-axis and it reaches the x-axis. And the reason for that is what I was saying on the earlier question, that if you can, when you're working out a gradient, if you can get the line to the axes, it's going to make reading the values just so much simpler, so much easier. So it's going to be change in y over change in x again. So delta y over delta x. Now, you can see it's a negative gradient, but I'm not going to put the minus value in this time. I've hopefully explained that you don't really have negative rates in reactions like this, so you just ignore the negative values. But I am recognizing it is a negative gradient. So my change in y, well, easy. I've got a 0, so that makes life a bit easier. So I just need to look at where crosses the y-axis, and that's 0.45, 0.46, and that is halfway, so 0.465. So my change in y is 0.465. And my change in x, again, life is made a little bit easier for me because I've gone all the way to the axis. I've got a 0 there, so I only really have to read this value. I think that is halfway along that square, so I have got, well, it's between 1100, halfway between 1100 and 1200, so that must be 1150. So I put those values in, 1150, and then I put that into my calculator, which I didn't actually do in advance, or I did actually, and it is 4.04 times 10 to the minus 4. So the rate that I've worked out is 4.04 times 10 to the minus 4. Now, we can, especially on something like this, we can draw our tangents slightly differently and still feel that they are a fair tangent, that they are really trying to touch the line at that one point. So in questions like this, where you're having to work a gradient out based on a tangent that you've drawn, they will have a range, or the answer, will be a range, and as long as your answer is within that range, then you're okay. So in this particular question, the accepted range was 3.70 times 10 to the minus 4 to 4.5 times 10 to the minus 4. So I am clearly within that range. So you obviously have to try your best to do the tangent as well as you can, as carefully as you can, but don't agonize that it literally has to be on the exact value that, say, the examiners have decided it has to be. Okay. And then we come to a 6-mark question, and in the actual exam this appeared in, I can't remember exactly what the average mark was in the country, but out of the 6 marks, I think it was something like 2.5. So fundamentally, people didn't do very well. So this is a very important question for us, because this is an example where a required practical, it might be where we actually have to explain how to do it, how we would do it. Now, I don't know whether it's better or worse, the fact that they've used letters. I'll let you decide that. But they've got here a general equation for a reaction is shown. A plus B plus C goes to D plus E. In aqueous solution, A, B, C, and D are all colourless, but E is dark blue. So our sign that the reaction has happened, I suppose, is the fact that the appearance of E will turn the solution dark blue. So what we're essentially measuring, or going to be, or what we can expect to be measuring, is the time it takes for the solution to turn blue. Now we have to read on. It says a reagent X is available that reacts rapidly with E. This means that if a small amount of X is included in the initial reaction mixture, it will react with any E produced until all the X has been used up. So why is that useful or important? Now, if we think about this reaction and we've got a color change, then we can probably approach this. We would probably expect to approach this as an initial rates reaction, i.e. we're going to measure the time it takes for a particular thing to happen, and the thing to happen could be that this turns dark blue. Now the reaction is going to start straight away, so that means E is going to be produced straight away, which means actually that you would expect it to turn dark blue, or almost instantly, which doesn't really help us. So what adding reagent X does is that it buys us some time. And as long as we add the same amount of reagent X to each version of the experiment we do, we are in effect, when I say buying amount of time, we're buying we're keeping something the same, right? So maybe buying time is not the best answer. Perhaps a better analogy would be that what we're doing is we're lengthening the distance of the race. So in every experiment, if we were comparing runners, and we wanted to know who was fastest and who was slowest, we would have a fixed distance. So let's say 100 meters. And so we would allow each of those runners to run 100 meters, and from that we would be able to determine who was the fastest, who was the slowest. And what X is in effect doing is providing that 100 meters. It's delaying. It's the faster that E is produced, the faster that X is used up, and then once X is used up, then E will remain, and that's when we get our color change. So the end of the 100-meter race is the equivalent of X having all been used up and E now suddenly appearing. So if we've got a fast runner, if we've got a fast reaction, then X gets used up much faster, and so E appears much quicker. If we've got a slow runner and the reaction is slow or slower, then it takes longer for X to be used up, so it takes longer for E to appear. So this is actually a very similar practical to the one right at the beginning of this question. If you think about it, this has got an A, B, and a C, and it goes to D and E, and that is essentially what we had at the beginning. And you also, if you think about it, if you added starch as an indicator, we would be able to recognize or see the appearance of the iodine. So actually, we could add something to this reaction that would be the equivalent of X, and we could time how long it took for that iodine to then go blue-black, or to appear and go blue-black in the starch indicator to work. So it's actually a very similar reaction. Anyway, we go back to it. So, how do we approach this now? We haven't read the final paragraph, have we, actually? So explain, giving brief experimental details, how you could use a series of experiments to determine the order of this reaction with respect to A. In each experiment, you should obtain a measure of the initial rate of reaction. So this very much is core practical 7 or required practical 7. So A is going to be our independent variable. It's going to be A that we change the concentration of. The thing that we're going to be measuring is the time it takes for the solution to go dark blue. That's because E is dark blue, and X is buying us, X has to be used up before we will get the solution turning dark blue. So we've got to make sure we put the same amount of X in each time. Our other control variable is going to be our other control variable is going to be B and C. So we need to make sure that that those are controlled, and so the only thing that we're changing is A. So also, how are we going to spot the color change? Well, again, if it's a very strong dark blue, then we can just say, it might be a sudden change, like an iodine clock. It could be a sudden change. It would probably be fair to do that. But the other way that you've measured how, when something can be seen or not seen is to use an X. So we could use an X, and so that once the cross is no longer visible, which is when it turns dark blue, that's when we could stop the clock. Because what we don't fully know at the moment is whether that dark blue change is very sudden or whether it's gradual. So whenever you're giving a method, I suggest you always use bullet points or numbers. I think that provides you with a sense of structure. It reminds you that you're giving a method, and I think it reduces waffle. So we've got quite a lot of things to add. So probably what we should add is everything bar A. and then we start the reaction, or we start the time once we add A. So if we go through our method, step 1, I guess you have to try and write it like a practical. I mean, you don't know what exactly what volumes to use. I think if you're just using sensible equipment and sensible volumes, I think that's fine. So using a measuring cylinder, measure, and like I say, we don't really know yet what they should be, but we'll just say 10 centimeters cubed of A, B, C, and X. So they are the 4 things that we are going to be adding together. And what we'll do is we'll place B, C, and X in a conical flask. So we're assuming at the moment that A affects the rate of reaction, or at least is certainly part of the reaction. So we'll just keep that separate for the moment. Trying to add all 4 and start the clock at the same time is not going to happen. So you can't add A, B, and C all together at this point, right? You're just getting things ready. Next, let's place the flask on a white tile. So that's what we're going to that's what we're going to have our cross on. So white tile with a black cross. And the other control variable, although to be fair, you're probably not likely to really think about this, but the other control variable here is temperature. And the easiest or the best way rather to control temperature in a reaction is to use a water bath. Now, if you didn't put the water bath in, I don't think that's the end of the world, but we'll do it as well as we can. So in a water bath, because we want to control the temperature, because otherwise that could affect the rate, so that the cross is visible. The cross is visible through the flask, or through the bottom of the flask. Okay. And then we're going to add A and start the timer. And we're going to time how long it takes for the cross to disappear. Okay. And then we're going to repeat steps 1 to 4. We're going to have to use the same volumes and concentrations of B, C, and X because they are our control variables, but we're going to change the concentrations of A. However, we must keep the same volume of A. That's because if we don't use the same volume of A, we're going to actually be affecting the concentrations of B, C, and X. Because we've added these different, these 10 centimeters cubed to each other, they are in effect diluting each other. So we have to make sure that the total volume is the same each time. Otherwise, we'll be inadvertently changing the concentration on for each reaction. So we're repeating steps 1 to 4. Using numbers here has been useful because I can just make that clear. Using the same volumes. Of B, C, and X, and different concentrations. So this is our independent variable, different concentrations of C. Sorry, of A, sorry. But they must still be 10 centimeters cubed because otherwise we're going to be changing the concentration of B, C, and X. So that's very important. That is a thing that comes up in other questions where you see water added. to some and not all. And the reason for that is it will be to keep the same total volume in the different reaction mixtures, and so that the volume of whatever you're changing is proportional in a sense to the concentration. That's probably confused you, so I'm sorry about that. Now, in this question, it's saying, explain, giving brief experimental details, how you could use a series of experiments to determine the order of this reaction with respect to A. So all I've done so far is give experimental details. What I haven't done is said how I can use the information that I'm gathering here, the time it takes for the cross to disappear. I can use that to work out the order of reaction. So we're nowhere near finished here. And one thing to take away from this is that when you're describing a reaction that yields results, if you know how to use how to use those results, then you must, and how they're going to tell you the information you need to know, you ultimately need to know, then you must include that. So if you think about the thermodynamics required practical, where you're measuring the temperature before you add a reactant, then the temperature after you've added the reactant over 15 minutes or so, you've got to talk about plotting temperature against time. You've got to talk about drawing the lines of best fit up to the point that you added the reactant. So you're drawing two lines of best fit, and then you're measuring the difference between those two lines of best fit at the point that you added the reactant to work out delta T. You must spell these things out. So for this one, I'm going to still stick with numbers. 1 over time is proportional to rate. So it's seconds to the minus 1. Rate is always proportional to 1 over time, or proportional to seconds to the minus 1. So what I'm going to, so if that's effectively rate, then I'm going to plot a graph of 1 over time, or rate, against concentration, against the concentration of A. So how does that time, that 1 over time, change against the concentration of A? And remember, 1 over time is proportional to rate, is in this effectively rate. That's still not enough, right? That shows what I'm doing with my results, but it hasn't shown how I've then used those results. So what you really need to do at this point is draw the possible shapes of the graphs and say, well, if it looks like this, then I know it's 0 order with respect to A. If it looks like this, I know that it's first order. And if it looks like this, I know that it's second order. You can say it in words, and I will write words, but what I would strongly advise you to do is, if you're ever trying to describe a graph, if you're ever trying to describe what you're doing with a graph, then I would sketch it. I would so sketch it, because that is going to be so much clearer, almost certainly, than anything you would write. So if the resulting graph is, and then I need to make these a bit thinner. So we're going to, so remember, I've got 1 over T against concentration of A. And if my line that I get is horizontal, then I know the rate is 0 order with respect to A. I'll come back and write their words in a second. If I actually want to be easier if I just copy this. If my graph looks like this, so it's proportional, directly proportional, or proportional, then that's going to tell me it's first order. So these are the shapes of the graphs you need to know. Just even let alone leaving aside this particular question, these are shapes that you need to know. And if my shape of my graph that I plot looks like that, then I know it's second order. So you need to spell these things out. So you could say, if the resulting graph is horizontal, then the rate is 0 order. And then just to be clear, WRT like that means with respect to. Okay, so with respect to A, if it's directly proportional, so then the rate is first order. And you should, be spelling out this with respect to A. Sorry, it's a bit cramped there. And then lastly, if it's continuously increasing, so that's how to describe the shape of that that final graph. If it's continuously increasing, then the rate is second order with respect to A. So that's quite a lot, isn't it? I'm sure there could be little gaps here, probably more on the experimental method, I guess. Although, you need to make it clear, it needs to be clear about control variables. It needs to be clear about how you're measuring. Right? There are probably the odd thing that you could have not included and still probably got 6 marks. These 6-mark questions tend to be described as stages. So you have to have stage 1 very good and stage 2 very good and stage 3 very good to get 6. So almost the stages are 2 marks each. The stages here, if I remember rightly, was the method was 1 stage, having a method that was going to give you valid results. What you then did with those results, I think, was probably stage 2, and then how you would interpret those results was stage 3. I think that was pretty much how it was. But this is a initial rates method. This is about measuring the time it takes to reach a particular point. The particular point here was the reaction mixture turning dark blue. We made sure that there was going to be some time before it turned blue by using X. X meant that even though the E was produced straight away, it was sort of recycled until X ran out. And then once X ran out, we got E appearing very clearly. In the mark scheme, however, there was a second method, and they clearly allowed it because it's in the mark scheme, and it could have got you 6 marks, although it wasn't an initial rates method. So I'm going to very briefly talk about it, but in a sense you can just freeze the video and read it. The other type of practical for required practical 7 would be continuous method. So initial rate is measuring the time it takes to get to a particular point and comparing those times. Continuous method is actually, like earlier on in the question, how does something change over time? The way you could have done it here, and it's not a bad method to know generally speaking actually, is to use colorimetry. So you can see that this is labeled in that stage 1, stage 2, stage 3 method. It is continuous monitoring or continuous method. It has very strong similarities. The difference is that you're not going to use X, although because X is the thing that allows initial rates to be used. It does say ignore, so actually if you'd used X, they wouldn't have penalized you, but actually X is not what you want to use. You want E to be slowly appearing and your colorimeter to measure how the concentration of E is changing over time. That's effectively what you're doing here by measuring the absorbance. So I would make sure you sort of appreciate that method. It's not, they can, the colorimetry can appear in transition metals. I think if it did, it would probably be a shorter answer than this. It would be about doing a calibration curve and so on. So colorimetry isn't a required practical as such, or isn't a required practical method, but is a method you can use in a required practical, and is a method that you can use when it comes to transition metals. But I hope that was helpful. You may have to listen to some bits of it a second time to sort of get quite what I was saying, but there was a lot in this question. It's a really good question to go through as preparation. And yeah, I hope that was of some help.